Welcome to the second day of our conference, and I take the occasion to again thank for the hospitality, the university and the organizers. And we start today with a talk by Giora Hon from the University of Haifa, and I think we all know each other, and you probably know how Giora is doing, I think, one of very best modes of history and philosophy of science.
Thank you very much. Good morning. I would like also to extend my thanks to, especially to JAUME and to the University of San Sebastian. This work, as you can see, is done together, co-authored with Bernard Goldstein of the University of Pittsburgh. In 1924, Robert Millikan, Nobel laureate in physics in 1923, foresaw a new era in physics in which the spectroscope would play the role of the telescope in seeking the consequences of what Millikan called the Planck-Einstein-Bohr law of radiation. And he writes, "Truly, we are just now entering upon a period of the fascinating study of the astronomy of the atom, a period in which the spectroscope is the instrument with which we must bring to light wonders no less fascinating than those which the telescope has revealed in the study of the stars." Although Millikan was right about a new era for physics, which in fact began in 1925, it had nothing to do with the astronomy of the atom. What made Millikan so confident that the planetary model was a true representation of atomic structure? Already in 1917, Millikan was persuaded by several sets of experiments that the electronic constituents of atoms are as small in comparison with the dimensions of the atomic system as are the sun and planets in comparison with the dimensions of the solar system. But there was more to this comparison. Millikan remarked further, "The evidence for the soundness of the conception of non-radiating electronic orbits is to be looked for first in the success of the constants involved, and if these constants come out right within the limits of experimental error, then the theory of non-radiating electronic orbits has been given the most crucial imaginable of tests, especially if these constants are accurately determinable." And he continues, "The extremely close agreement of experimental results with quantum theory constitutes the most extraordinary justification of the theory of non-radiating electronic orbits. It demonstrates that the behavior of the negative electron in the hydrogen atom is at least correctly described by the equation of a circular non-radiating orbit. If this equation can be obtained from some other physical condition than that of an actual orbit, it is obviously incumbent upon those who so hold to show what that condition is. Until this is done, it is justifiable to suppose that the equation of an orbit means an actual orbit." And Millikan added, "Again, the success of a theory is often tested by the exactness of the fit between calculated and observed results. The theory of electronic orbits has had remarkable success of this sort." For Millikan, a theory may be deemed successful because the calculated results fit the observation to a high level of accuracy. It is striking that Millikan thought that the success of the theory based on the planetary model of the atom, that is Niels Bohr's theory as modified by Arnold Sommerfeld, had been confirmed merely by numerical correspondence of a limited range. Millikan demonstrated to his own satisfaction the accuracy of the theory when the numerical consequences calculated from it are compared with known constants. This perfect matching for the hydrogen atom convinced him that the orbit is not just a mathematical abstraction, Rather, it is an actual orbit. In 1917, Millikan acknowledged the possibility, at least in principle, that another theory might be as good as that of Bohr-Sommerfeld, but he did not really expect such a theory to be formed. He writes, if the test of truth in physical theory is large success both in the prediction of new relationships and in correctly and exactly accounting for old ones, the theory of non-radiating orbits is one of the well-established truths of modern physics. For the present, at least, it is truth, and no other theory of atomic structure need be considered until it has shown itself able to approach it in fertility. I know of no competitor which is yet even in sight, writes Millikan. Millikan's triumphalist tone is worth noting. He used terms such as success, justification, success of a theory, and agreement constitutes the most extraordinary justification of the theory. And then he adds truth is added to the vocabulary, namely one of the well-established truths of modern physics. Evidently, Millikan had great confidence in the Bohr-Sommerfeld theory and could not imagine a theory of atomic physics which is not based on the planetary model. What was the ground for Millikan's confidence? We identify the methodological principle upon which he based his assured claim. It is the prediction of new relationships and correctly and exactly accounting for old ones. And this is confirmed in the exactness of the fit between calculated and observed results. However, this methodological rule can lead to confirmation of false theories. As it happened, what Millikan thought was improbable actually took place. For later, theories were able to capture this success without appealing to a planetary model. In effect, as we now know, Millikan's confidence in the theory based on his experimental results was unwarranted. Early in December 1923, Werner Heisenberg wrote to Sommerfeld that, I quote, when one contemplates what has really been done in atomic physics, one sees clearly that mechanical model conceptions have no real meaning. The orbits are not real, neither with respect to frequency nor energy. And exactly a year later, Wolfgang Pauli wrote to Bohr that, and I quote, we should not want to clap the atoms into the change of our preconceptions, to which, in my opinion, belongs the assumptions of the existence of electron orbits in the sense of the usual kinematics. But we must, on the contrary, adjust our ideas to experience. As is well known, both Heisenberg and Pauli belong to the vanguard of physicists who in 1925 undermined the astronomy of the atom and helped construct a new theory altogether devoid of any picture or model, let alone a planetary one. The case of Millikan is a fine example in which confidence in a theory was based on the surprising predictive power over a limited range and on a most appealing pictorial analogy. In this paper, we focus on the misleading sources of confidence in the quantum theory. We are concerned here with the issue of confidence, which is historically and philosophically. For this purpose, we first offer an overview of the development of the Bohr-Sommerfeld theory with special attention to the astronomical model, and we conclude with a few reflections on the general issue of confidence in a physical theory. What is the geometrical shape of the path of an electron in motion? Or better, how should one picture the path of a free electron? Obviously, no one asked this question before the discovery of the electron at the end of the 19th century. But even after its discovery and the development of theories of the electron, which addressed many sophisticated issues concerning the physics of the electron, no one perceived any particular difficulty in characterizing the path of an electron in motion. For instance, Max Abraham, in his paper of 1902 on the dynamics of the electron, and Albert Einstein, in his theory of special relativity in 1905, talk of a Bahn in German, a path, without saying anything more specific. For another example, in 1908, August Righi invoked the expression, the trajectory of an electron, in a study of interactions among electrons, ions, atoms, and molecules, again assuming the concept of trajectory without any discussion. The geometrical form of the path of a free electron as it moves in empty space was not considered problematic at the time. The issue, however, had to be addressed once a bound electron confined to the atom became the object of study. Given that the atom is a stable and electrically neutral system, and that the electron, a charged component of this system, is not stationary, what is the geometrical form of the path of the electron in motion within the atom, such that the atom can radiate and still remain stable and electrically neutral? This is certainly a fundamental problem for which there was no immediate solution. The obvious methodological move when something new is confronted is to appeal to analogy. As John North put it, an explanation of the unfamiliar by the more or less completely familiar. The mechanical model for the atom, that is the planetary model, is one such case. Probably the most stable, well-studied mechanical system with constituent moving elements in the planetary system is the planetary system. The term orbit had been used in astronomy since it was introduced by Johannes Kepler in the early years of the 17th century, and without much discussion, it came to be applied to the path of the electron within the atom. For example, Paul Langevin, of whom we've heard yesterday, began his paper of 1905 on magnetism and the theory of the electron with the following assumption. He writes, Langevin, let us suppose some electrons in motion in the interior of the molecule following closed orbits that can be considered similar to closed currents circulating along these orbits from the point of view of the magnetic field produced at a distance. It is important to realize that a fundamental assumption is made here. The bound electron, as distinct from the free electron, is assumed to be moving in a closed orbit. No argument is offered to support this claim, and equally there is no reference to a planetary system, although before the discovery of the electron, the term orbit in physics had always been associated with a planetary system. In other words, Langevin set up the discussion silently within a mechanical context whose paradigm is a planetary system. This theoretical framework seems to have influenced Bohr in the development of the quantum theory. The idea was that atoms resemble a planetary system, that is, central nucleus corresponding to the sun, with electrons rotating around the nucleus in orbit like planets around the sun, such that almost all of the atom is empty space. We suggest threefold periodization for appeals to planetary analogies, modeling, and terminology in order to highlight the multifaceted historical development of atomic physics and to raise philosophical issues. In the early period prior to 1915, the planetary analogy and modeling were of limited usefulness, but they opened the way to a theory that had all the marks of success. In 1901, Jean Perrin, Nobel laureate in physics in 1926, proposed the planetary analogy for the atom, and it is most likely that he was the first to do so after the discovery of the electron. Then a series of physicists, some of them leaders in the field, such as J.J. Thomson, considered the motion of the electron within the atom in various planetary configurations, for example, as rings of electrons. The title of Thomson's paper of 1904 is On the Structure of the Atom, and it is noteworthy that he appealed to planetary terminology. For example, Thomson invoked the term orbit in his discussion of the stability of the atom, implicitly appealing to planetary conceptions. But there is no picture to illustrate these rings and no detailed analogy with any mechanical system. This first phase ended with Bohr's celebrated theory of 1913, in which, somewhat in the manner of Thomson, planetary terminology is applied without any explicit reference to a planetary model. Bohr's quantum theory did not immediately have a major impact on the world of physics. Its reception, however, accelerated with the commencement of the second phase. This phase began in 1915 with the work of Sommerfeld, who argued for an atomic analog to Kepler's 3 laws of planetary motion within the framework of Bohr's theory. The equation for the energy of the Keplerian motion that follows from the action integral is so precise and fruitful, Sommerfeld said, that it could be an algebraic accident, that it could not be an algebraic accident. He writes, the result was surprising in the highest degree and of striking certainty. The energy is then uniquely determined by the sum of the quanta of action, which we may distribute arbitrarily among the azimuthal and radial coordinates. It seems to me impossible that such a precise and fruitful result could be attributed to an algebraic accident. Rather, I see in it a persuasive justification for the extension of the quantum approach with respect to the radial coordinates to the application of this approach separately to both degrees of freedom in our problem. Evidently, Sommerfeld had great confidence in his generalization of Bohr's theory based on a methodological rule similar, as we have seen, to the one which Millikan based his claims. For our argument, For our argument, it is important to note that Sommerfeld's generalization is based on deepening his commitment to the planetary model. That is, the scheme is planetary and specifically Keplerian, a novel conception for the atom at the time. Sommerfeld conceived the atom as a closed mechanical system in which only internal forces act. At stake was the dynamics of this mechanical system. The question arises, he writes, Sommerfeld, how can the electrons of the atom maintain themselves in opposition to the attractive action of the nuclear charge? Will this action not cause them to fall into the nucleus? The answer, a possible one, which is particularly simple and satisfactory, is furnished by the condition of the solar system. Sommerfeld transfers the problem of stability of the atom to the stability of the solar system. He writes, the Earth fails to fall into the Sun for the reason that it develops centrifugal forces owing to its motion in its own orbit, and these forces are in equilibrium with the Sun's attraction. If we transpose these ideas to our atomic model, we arrive at the following view, and he stresses the following sentence. The atom is a planetary system in which the planets are electrons. They circulate about the central body, the nucleus. The gravitational attraction, as expressed in Newton's law, is represented by the electrical attraction as given by Coulomb's law. These laws are alike in form. The imagery is quite extraordinary. Sommerfeld, in so many words, identified the atom as a planetary system. The stability of the atom is due to the same conditions that maintain the stability of the solar system, so his argument goes. Moreover, for Sommerfeld, it is not merely an analogy, for he states an identity. The atom is a planetary system. This is, of course, an exaggeration expressing enthusiasm, surely a sign of Sommerfeld's confidence in the model, rather than an objective analysis. And Sommerfeld retreated immediately to the analogy. The gravitational force is represented by the Coulomb force, the two laws being alike in form. Sommerfeld was aware of the differences And although the laws are formally similar, he writes, there is a difference in that the planets repel one another in our atomic microcosm. Likewise, according to Coulomb's law, whereas in the case of the solar macrocosm, they undergo attraction not only from the sun, but also from themselves. Still, the claim that the dynamical laws hold in atomic microcosm exactly as in the solar macrocosm runs like a thread in Sommerfeld's study. Sommerfeld elaborated this analogy in his influential book Atombau und Spektrallinien, and the first edition in 1919, we've seen this yesterday. In this second phase, the planetary analogy became strong with quantitative and experimental consequences and took advantage of recent development in relativistic physics. Bohr accepted Sommerfeld's planetary atom model and lent his authority to support it, most prominently in his Nobel lecture of 1922. No doubt, under the influence of Sommerfeld, Bohr now explicitly described the atom as a planetary system and described it as a picture, which bears a striking resemblance to a planetary system such as we have in our own solar system. And Bohr immediately drew an inference from his analogy. Just as the simplicity of the laws that govern the motions of the solar system is intimately connected with the circumstances that the dimensions of the moving bodies are small in relation to the orbits, so the corresponding relations in atomic structure provides us with an explanation of an essential feature of natural phenomena insofar as these depend on the properties of the electrons. That year, 1922, probably marks the high point of the planetary model. Bohr, however, noted that the analogy provides us with an explanation, but it has its limitations. As soon as we try to trace a more intimate connection between the properties of the elements and atomic structure, writes Bohr, we encounter profound difficulties in that essential differences between an atom and the planetary system show themselves here in spite of the analogy we have mentioned. The motions of the bodies in a planetary system, even though they obey general law of gravitation, will not be completely determined by this law alone, but will depend largely on the previous history of the system. Thus, the length of the year is not determined by the masses of the sun and the earth alone, but depends also on the condition that existed during the formation of the solar system, of which we have little knowledge. The definite and unchangeable properties of the elements demand that the state of an atom cannot undergo permanent change due to external actions. We may formulate the difference in this way. Mechanical stability has memory. It records mechanical disturbances and retains their influence. Atomic stability, by contrast, can undergo all sorts of interactions, but the atom of some element will always remain the same with the same physical properties unless it is transmuted into another element. Notice that Bohr speaks of a picture of the constitution of the atom, a picture which, given his analysis, cannot be retained. The assumption that the laws governing the macro world can be used to explain the micro world of the atom reflects a strong intuition which until the early years of the 20th century had proved itself productive even quantitatively. But then uneasiness began to be expressed, not least by Bohr himself. The planetary model, with its mechanical worldview, so perspicuous intuitively, could not account for cases where motion of several electrons are involved, like in helium. In the third phase, Max Born took the lead. Indeed, he is largely responsible for calling the new theory quantum mechanics, an expression that had been coined by Einstein. In July 1923, the scientific journal the Naturwissenschaften, mark the 10th anniversary of Bohr's path-breaking paper on atomic structure. In addition to including Pauli's German translation of Bohr's Nobel lecture, the journal published Born paper, Quantum Theory and Perturbation Techniques, whose goal was to extend the underlying mechanics by introducing a new method borrowed from classical mechanics. Born opened the paper with the following claim. One of the most remarkable and active results of Bohr's atom theory is the idea that the atoms are miniature planetary systems. The thought that the laws of the macrocosms are reflected in the small earthly world apparently exercised a great enchantment on the human mind. Already Bohr's first great success rested on the application of the Keplerian laws of planetary motion to the hydrogen atom that consist of a nucleus with electrons circulating about it. Bohr stated that he intended to borrow the technique of perturbation theory. Given the assumed similarity between the planetary system and atomic structure, it appeared reasonable to turn to mathematical method used to address many body problems in astronomy and to apply them to the study of the structure of the atom. Bohr proceeded to examine the applicability of perturbation theory developed in celestial mechanics to the study of the atom. However, perturbation theory, as Bohr noted, proved unhelpful in solving the problems of the planetary model of the atom. The thrust of Bohr's conclusion is that there is little hope that mechanics can produce the answer for atomic structure. The road to the solution was not yet clear in 1923, but Bohr ended this paper with guarded optimism. He writes, "In any event, we can see that the similarity of atoms to planetary system has its limits. The agreement between the two systems is exact only in the simplest case. But the progress of quantum theory cannot be stopped by this. Rather, it will acquire new strengths from the resolution of the present contradiction." Bohr's critique of 1923 contrasts with Millikan optimism in 1917, and above all, the confident tone of Bohr's Nobel lecture in 1922. The Bohr-Sommerfeld model of the atom, which was essentially based on the planetary model, began to lose credibility in 1923 when physicists, included Bohr, attempted to extend the quantum theory to atoms of atomic weight greater than hydrogen, such as helium. Several modifications were suggested, but no new theory successfully challenged the planetary model. Indeed, a series of responses to the failure of the quantum theory were published. The planetary model for the atom was thus rejected before there was a successful theory to replace it. Given the belief in the universality of Newtonian mechanics, it is hardly surprising that the structure of the atom was compared to that of a planetary system. Nevertheless, from the outset of formulating atomic physics, it was clearly perceived and explicitly noted that the atom exhibits categorically different kind of stability from that of a mechanical system. To be sure, the planetary system is probably the most stable mechanical system known to man. But as a contingency, it cannot, in principle, be related to the inherent necessity of the stability of the atoms, the building blocks of matter. However, confidence in the planetary model was greatly enhanced by its success in explaining and predicting phenomena of simple atomic structure. This success made it seem likely that a fully satisfactory theory of this nature would be found in the near future, although later it became clear that this initial optimism was ill-founded. We distinguish between confidence and confirmation. The latter is the subject of a vast literature in philosophy of science. It concerns the relation between evidence and theory. In what ways and to what extent does the evidence support the theory or hypothesis. One may identify three conceptions: qualitative, comparative, and quantitative. The first simply states that evidence E confirms hypothesis H. The second claims that E confirms H more than H prime. And the third conception, the quantitative, calculates the degree to which E evidence confirms H in probabilistic terms. If a theory has been confirmed, there may no longer be reason to doubt it, whereas confidence in a theory will vary by the individual scientist who weighs the evidence idiosyncratically, given certain predispositions which are not always conducive to probabilistic measure. This is akin to scientists ignoring anomalies, that is, confidence in the theory is generally not shaken by a few anomalies. We are not engaged here with the formal analysis of probabilistic relation between evidence and theory. Rather, we characterize the attitude which scientists take vis-à-vis a theory under scrutiny. This is the conception of confidence. It is not surprising that close agreement between experimental data and the consequences of a theory leads to confidence in the theory. We thus invoke confidence as an epistemic disposition which, however, is not related to degree of belief. Confidence is what keeps a scientist focused on improving a theory so that the theory, as modified, can be confirmed by future experiments. It therefore expresses expectation. It is worth investing time, effort, and material resources in work on the theory or not. Confidence in the current state of theory, confidence in the current state of a theory is then associated with the expected future success of the theory, possibly with some minor modification over a broader range of phenomena. Unfortunately, some scientists have extended their confidence in a theory based on numerical agreement to claim that it is a true description of nature, but that claim is unwarranted, as we have seen. Numerical agreement of theory and experiment is simply not strong enough to support such claims. And implicitly or explicitly, the metaphysical power of a pictorial model has on occasion reinforced the confidence of scientists in a proposed theory and made them reluctant to discard it. Thank you.